Picking up on our volcano story, we're going to focus for a bit on Yellowstone National Park in the western United States. Most of the park is located in Wyoming, but a little bit of it splashes over into Montana and Idaho as well. The park gets its name, Yellowstone, from the Grand Canyon of Yellowstone, which you see here. This is a thick sequence of rhyolite. Therefore, it is the result of a very, very explosive eruption. It took place about 640,000 years ago. This massive eruption deposited 1,000 feet of rhyolite here in the canyon, over 300 meters in international terms. And since that time, the Yellowstone River has cut down through the canyon, forming this multicolored view you get from Inspiration Point. Now, in order to understand what's going on in Yellowstone today and better predict what's going on in the future, we need to take a look at what this Yellowstone hotspot has been doing up to this point. Currently, the hotspot is located here beneath Yellowstone Lake, and we can see that it's transected across the country, across southern Idaho, and then up into Oregon and Washington, and then to the Pacific coast. So the transect taken by this hotspot is roughly like this. And currently situated right here beneath Yellowstone. Now, usually every 2 to 3 years, my mom and my stepfather see a documentary on a super volcano of Yellowstone Park, and that's when I get a text message. Is it safe to go to Yellowstone this year? And I tell them every year, as long as you leave the bison alone, stay away from the grizzlies and the moose, and the traffic, you'll probably be okay. If you're worried about volcano safety, then you got about 150,000 years, we hope, before the next big eruption takes place. And it will be a very, very big eruption. What we can see looking back at the volcanic rocks that were deposited by the migration of this hotspot, we see that the most recent eruption again took place about 640,000 years ago. There are smaller eruptions that took place around the West Thumb 70,000 years ago. But tracing back to more major eruptions, we can see a 4 to 6 million year old sequence here, 10, 11, 12, 14, 15 million years ago. And we also see that this transects away from this banana-shaped feature, Snake River Plain, which was also the location of Lake Idaho, the Miocene through the Pliocene. Now, geologists have named these events the Yellowstone Plateau volcanic event that took place 640,000 years ago, generating the canyon. It is the most famous. As we go back in time, we hit other significant eruptions, the Peekaboo eruption, Hagerman Twin Falls eruption, and one we'll focus on for a few minutes here, the Bruno Yarbridge volcanic events that took place from 12.5 million years ago to about 11 million years ago. And what this did, this eruption that took place here, generated a very significant ashfall far, far away. And this particular ashfall led to what's called the Bruno Yarbridge Ashfall in Nebraska. It's a park now that displays the animals that were killed during this eruption that took place 1,000 miles away. So let that be a warning to you. You can be 1,000 miles away from Yellowstone when it erupts the next time, but you might end up like this. So this is a Teleoceras. It is a early rhino-like animal. It was buried in ash when these lava flows were active in the Bruno area. This is Bruno Canyon in southwestern Idaho. And here I'm overlooking the Snake River Plain and some of these volcanic deposits with Jerry Smith. He was one of my PhD advisors at the University of Michigan. So this is about 10 years ago. We were looking at some fish fossils that are recovered between these volcanic ashfall events within the Snake River Plain deposits of Lake Idaho. And what does this ash look like? It looks like sand, but zooming in, it is glass with lots of little bubbles or vesicles in it. And you know, when you break glass, you get sharp edges. So in this case, we're breaking glass with lots of sharp edges. This makes breathing difficult. It's bad for your vehicles. It gets sucked into the engine and it grinds away at the parts inside your car. And it makes shopping difficult. I don't know why they're carrying a shovel with them, but I guess they're ready for the next ashfall. So these are photos from the Mount St. Helens event in 1980, relatively minor volcanic event. And this is what an ashfall event would look like in the modern world, or what it does look like in the modern world. So you can see that it flattens the vegetation, the weight of the ash. Again, this is mineral grains and glass that are weighing down this vegetation. Ultimately, it's going to kill it. Any animals that inhaled too much of this ash are also going to perish. In the case of the Yarbridge ashfall event, the bones of the animals indicate that they died from lung failure, from inhaling this volcanic ash, these shards. It's like inhaling tiny broken light bulbs. Smaller animals that have a lower lung capacity would have died first, and larger animals would have hung on a bit longer. We do find evidence of bite marks on some of the bones, and this indicates that some animals survived the ashfall, the initial destruction, and preyed upon the remains of animals that succumbed to the ashfall. But we haven't found any predator remains as of yet. One of the more famous animals of this sequence is the Aleurodon. It's a bone-crushing dog, or bone-crunching dog, that would be similar to a modern hyena. Very strong jaws, very robust teeth, can essentially crush any bone to get the marrow out. Now, what geologists do is conduct a chemical analysis of volcanic ash that allows them to match the ash event to an eruption. We do this in the modern day with ice cores. If we see a climatic event that may be tied to a volcanic event, we measure the grains of material in the ice core and try to match that to a volcano somewhere in the world. And if there's a match, that implies that there may be some causality. The eruption may have caused that climate event. So for comparison's sake, here we have a modern adult male gray wolf. This is a dire wolf. You may have heard of them. Slightly larger Pleistocene species of, or modern wolf. And then the Aleurodon, back in the Miocene and Pliocene, would have been pretty similar in size to a gray wolf, about the size of a large German shepherd. And this is a Teleoceras, proto-rhino-looking animal, kind of squat, seen here in action. These are nearly perfectly preserved by the ash. In fact, this event is rare in geologic time. It's called a Lagerstätten, a German for place of storage. You heard of the type of beer called a lager, like Budweiser? That implies that it's been stored in a cold basement. That's the style of production of that type of beer, the lager. In this case, Lagerstätten means very, very exceptionally well-preserved organisms. They're usually articulated skeletons. The bones are all in place. They're still connected. And soft tissue may be preserved as well. So what do we find in the ashfall in Nebraska? Well, we find 5 species of equids. Horses evolved in North America and then went extinct in North America. Now, interestingly, maybe surprisingly, these camels evolved in North America and then spread around the world, went extinct in North America. The modern species of American camels are all found in South America. Alpaca, llama, guanaco, and vicuna. They're all famous for their defensive spitting technique. Subsequently, you may have heard of the brief camel experiment in British Columbia. A bunch of them were imported for the mining trade, but apparently the smell and the astonishing appearance led mules from other prospectors to jump off of the trail to their death. So camels were discontinued. They were turned loose. They persisted around Lillooet for a few decades, perhaps, and now have all disappeared. But there's a bridge named after them. Other species, interesting species, include the saber-toothed musk deer. This is a musk turtle. In the modern world, they're called musk turtles or stinkpots. And early rhinoceros, 3 species of canids, including the Aleurodon that we talked about earlier. Tortoise, a hawk that looks like a modern secretary bird, and a crowned crane. This was all generated by the same hotspot that has produced Yellowstone Park today. If you get a chance to get to Yellowstone Park, I highly recommend it. Plan on spending a few days there, but get organized because it's a nightmare. There are so many people from everywhere on Earth there all the time doing less than reasonable things. So watch out. Make sure you have a campground months in advance or a room nearby. There are a couple places you can stay just outside the park: West Yellowstone, the north entrance near Gardner, the northeast entrance, Cook City, Silvergate, Cody's not too far away. So there are places to stay outside of the park. So this caldera is 55 by 75 kilometers in diameter. Last erupted explosively 70,000 years ago, and it overlies the current position of the Yellowstone hotspot. Over the last 2 million years, since the hotspot became located about here, Yellowstone has ejected 8,000 cubic kilometers of material. Today, one of the most recognizable features of Yellowstone, one of the draws for tourists and scientists around the world, are the hot springs. And these hot springs, you can see here, this is near Grand Prismatic Hot Spring, which we'll see again in a few minutes. What we have is buildup of kind of reefy material here by cyanobacteria. These are called hyperthermophilic bacteria. That means they can withstand high temperatures, and the temperatures range from boiling to room temperature. In this case, the room being Yellowstone in the summertime, so about 20 degrees centigrade. This color transition you see here is related to the temperature. The bacteria that can withstand the highest temperatures are bluish, and the bacteria that are most sensitive to high temperatures are going to be red and brown. So cool out here, warm here, hot here, very hot here. There was a guy that jumped in one of these about 3 years ago. Him and his sister went what was called hot potting, apparently. I didn't know about it until the report came out. But he jumped in or fell in, and he was boiled alive. And by the time his sister got back with the rangers, he had dissolved. So that was that for him. There was literally no trace left of him after a short period of time. So no hot potting if you go to Yellowstone Park. Also famous in Yellowstone are the geysers. So I took this guy a couple years ago. We were down in Idaho to see the eclipse and made a run over to Yellowstone Park, catch the eruption of Old Faithful, which you can see right back here, bubbling between eruptions. It used to go off pretty faithfully every 65 minutes or so. Then there were a series of earthquakes in the 80s and 90s, kind of jumbled up the plumbing system. And now it goes off at a much wider range of times, somewhere between a half hour, hour and a half. Still pretty regular for a geologic event, but not quite the kind of eruption you can set your watch by. So here we have the simultaneous eruption of Old Faithful, relatively minor eruption, and the Beehive Geyser, which is located just over here. I've only seen this go off once, but it was at night, no pictures. It was pretty surprising to be next to it, though, when it went off. This is one of the more famous sites. This is Grand Prismatic Hot Spring. And you can see people for scale here on the walkways. If you're in Yellowstone or when you're in Yellowstone, stay on the walkway. Every year somebody steps off the walkway and falls through the crust and gets boiled alive as kind of a tourist spectacle. So stay out of the water, stay on the sidewalk. Again, you'll see the zonation here. The hot algae in the center where the water's hottest, cooler algae in the green zone, cooler still in yellow, and then the reds and the browns are the coolest. Now this is still pretty hot water. I'd guess it's probably around 50, 60 degrees centigrade when it flows under the sidewalk. This is very hot. It's at the boiling point of water, which is at this altitude, probably around 95 degrees, something like that. Now, when Yellowstone goes off in a big way, as some other volcanoes have in the past, it's going to generate an ashfall that covers a very significant portion of North America. So here we see the Yellowstone ash that was erupted 665,000 years ago, about the same time that the rhyolite was deposited, making up Yellowstone Canyon. This ash blew all the way across North America to the East Coast, and it shows up significantly in various deposits within this dotted line. Now, the Long Valley caldera in Central California also produces very large ash clouds. In this case, this was 760,000 years ago. Crater Lake, which we'll see photos of later, produced the Mazama ash about 7,600 years ago. This was picked up here in Kananaskis country in southern Alberta in one of our lake cores. So we're able to use the chemistry of this ash to define that layer in the core as being 7,600 years ago. Mount St. Helens, the 1980 eruption, which was a big deal, generated this tiny little plume of ash. So almost nothing compared to these other events. And this, again, was a very big deal to anyone living in this area in 1980. Now, Mount St. Helens has been much more violent in the past. 3,800 years ago, it generated this plume of ash. So again, we find this in a lake up here. We can use this layer as a free age. Not quite free, but less than carbon dating anyway. So when Yellowstone goes off again, it is going to be a big deal. Here is an estimate of the influence of ash on North America in millimeters. So all the way out into the central Atlantic, we're going to get 1 to 3 millimeters of ash. So Bermuda is going to get ash from Yellowstone. Closer to Yellowstone, we're going to get over 1 meter of ash, and right next to the eruptive event, probably many, many meters, maybe another 300 meters, like we saw in the Grand Canyon of the Yellowstone. So again, this will be a very big, totally disruptive eruption. If the United States is still around, this could be the end of it. If Canada is still around, also it could be the end of Canada. Again, size matters and the explosiveness of the event matter. The Eyjafjallajökull eruption in May of 2010 generated a fairly wimpy little plume, similar to the Mount St. Helens plume. This didn't get very high into the atmosphere, and it was quickly blown away, streamed off to the southeast. Mount Pinatubo, which erupted in 1991, generated a much larger plume, and it was able to punch its way up into the stratosphere and spread out as a giant mushroom cloud here. So the Eyjafjallajökull event, we see a small streamer. In Pinatubo, a big plume, big cloud. Okay, we've been talking about volcanic deposits and lavas. What do these look like when we get up close? We're going to use texture of volcanic rocks to identify them. These are going to reflect the conditions under which they crystallized or formed. So they're going to tell the story of the rock itself. These rocks may include vesicles. These are holes that are left by gases that were present when the rock solidified. They may have glassy texture. This is when a substance cools so fast that it can't get organized into a crystal lattice. So you have an amorphous crystal, just like glass. And we may have pyroclasts. As you might imagine, clast means a particle or a bit, a piece, and pyro means fire. So fire particles or fire chunks. Here are some examples. This is a basalt that was very gassy, and again, as this basalt solidified, those gas bubbles remain as open spaces in the rock. We can have pyroclastic deposits that include volcanic ejecta, material that's blasted out of a volcano. If it's fine-grained, we'll call it an ash. If it's dangerous in size, we call it a bomb. We have pyroclastic flows. These are volcanic tuffs and breccias, a mixture of particles with gas and sometimes liquids. These can move very, very fast, hundreds of miles an hour. Here we see an eruption in Costa Rica. It's a pyroclastic eruption from Mount Arenal a very famous volcano in Central America that's erupting almost continuously. When I first visited, we were in the village of Arenal, which is right next to the volcano. It was pouring down rain and foggy, cloudy, and we could hear the volcano in the distance, the rumbling sound, broom, broom, an occasional boom. So, we're having a beer on the balcony overlooking the village, and we hear one of these booms. We thought, wow, that was a pretty big one. Then about 4 seconds later, the sound of a giant metal dumpster crashing through a galvanized steel roof filled with bowling balls. And that was a volcanic bomb that hit one of the awnings near us. So we thought we'll just go back inside until the rain stops. Here's an example of a volcanic bomb, a Cooper Mini-sized volcanic bomb. And here we have a close-up of volcanic tuff. These tuffs consist of very fine-grained material, and you can see some laths of crystals. Things like selimonite might be present in these breccias or tuffs. And this is a volcanic breccia. Angular grains of a wide variety of sizes. This is the immature or unweathered version of a conglomerate. A breccia is a conglomerate-like rock, but instead of rounded cobbles, pebbles, boulders, and sand grains, we have angular cobbles, pebbles, boulders, and sand grains. Now, some examples of pyroclastic flows and pyroclastic debris can be found here. Some very famous examples include that of Pompeii.